Welcome back to QHSE Talks.
Glad to be here.
You know, it is genuinely, it's wild to think about how we navigate the world every single day. Just completely ignoring the most relentless, unforgiving force on the entire planet.
Right. You're talking about gravity.
I am absolutely talking about gravity. I mean, we don't really think about it when we are just, walking down the street to grab a coffee or whatever.
Yeah, you're tripping it, maybe you scrape a knee and you just move on.
Exactly, you move on. But when you are working 20 or 50 or even 100 feet up in the air on a job site, that invisible force becomes this constant lurking hazard.
It's always there.
Always. And we honestly just don't respect it enough. But today, we're going to force ourselves to look that invisible hazard right in the eye.
Which is so important.
It really is. So if you are listening to this right now, maybe you are deep in the trenches prepping for your ASP.
The Associate Safety Professional exam.
Right, your AST exam. And you are probably staring down an absolute mountain of formulas, wondering how you are ever going to memorize them all.
It can be super overwhelming.
Or perhaps you're a seasoned safety professional out in the field right now, and you want to deeply, truly understand the critical math behind how the equipment on your site is actually saving lives.
Which is what it's all about.
Exactly. So whatever brings you here, this edition of QHSE Talks is custom tailored for you.
Yeah.
We are going to make this math actually make sense.
That is exactly the goal today, because when we talk about fall protection in the safety industry, there is this really dangerous tendency to treat it as just an administrative task.
Oh, like a check the box kind of thing.
Yeah, exactly. People think it is just about, flipping through an equipment catalog, buying a compliant harness, handing it to a worker, and checking a box on a clipboard.
Right.
But it is so much more than that. I mean, we are talking about mastering kinematics here.
The actual physics?
The literal physics. We're pitting fragile human physiology against the unforgiving constant acceleration of 32.2 feet per second squared.
That's a brutal battle.
It is a brutal battle of physics. And the harsh reality is, if you don't know the math, and if you don't design your systems around that exact math, gravity wins every single time.
Wow, yeah. That is a sobering way to look at it, but it's the absolute truth. So the mission of this QHSE Talks is to thoroughly explore ASP Domain 1 Topic 7.
Which is all about calculating fall protection parameters.
Right. We are going to unpack the terrifying reality of what gravity actually does to a human body in free fall, the intense physics of deceleration, and the exact, precise formulas safety engineers use to prevent a slip from turning into a tragedy.
It's heavy stuff, but it's vital.
It is. So let's just jump right into the physics of it, because before we can even begin to pull out our calculators and design a system to protect a worker, we have to understand what is actually happening in the physical world the very moment a worker loses their footing.
Right. We have to start at the literal beginning of the fall. And to do that accurately, the very first thing we have to do is just strip away all the Hollywood myths we've been fed our entire lives.
Oh man, the movies have ruined our perception of this.
Totally ruined it. Think about every action movie you have ever seen, right? A character slips off the edge of a skyscraper or a cliff. They fall for a bit. They look surprised.
They usually scream a little.
Right. They yell, and then miraculously they shoot a hand out and grab a dangling rope or the edge of a metal railing to save themselves.
Like it's nothing.
Exactly. And that cinematic trope has created this massive, subconscious, false sense of security in the real world.
People actually believe they can catch themselves.
They genuinely believe that if they slip, their reflexes will just kick in and save them. But the human nervous system simply does not operate fast enough to beat gravity.
I'm so glad you brought that up, because I was reading through the Yates Safety Professionals reference and study guide from our sources, and there was a statistic in there that completely destroyed my understanding of human reflexes.
It's eye-opening, isn't it?
It absolutely shatters that whole, I'll just grab the rail myth. The text states that it takes about 1/3 of a second for a human being to merely become aware that they are falling.
Just let the physical reality of that sink in for a second. 1/3 of a second.
That feels so fast, but it's really not.
No, it's not. That is the time it takes just for the fluid in your inner ear, your vestibular system, to slosh around, realize you are in free fall, and send a panic signal up your nervous system to your brain.
Basically saying, hey, we have lost our balance and we're no longer supported by the ground.
Exactly. And in that 1/3 of a second, your body has already yielded to gravity. You haven't done anything to stop it. You just barely know it is happening.
Right. And the text says it gets even worse. Because once the brain is finally aware that you are falling, It has to formulate a survival plan, right?
Yes. It has to encode that plan into electrical signals.
Right, and send those signals down your spine to your muscles to actually execute an action like reaching out your arm and closing your hand around a guardrail.
And according to the text, that physical reaction takes another 1/3 of a second.
Exactly. So if we put that together, you are looking at roughly 2/3 of a second of total elapsed time before your body can even begin to physically attempt to arrest its own fall.
And in the world of kinematics, 2/3 of a second is an absolute eternity.
It really is.
Yeah.
Here's where it gets really terrifying. During that brief 2/3 of a second window, the time it takes you to blink, process the slip, and reach your hand out, how far do you actually fall?
It's a shocking number.
It is. The Yates text explicitly notes that in that specific fraction of time, the falling employee will have already fallen at least 21 feet.
21 feet. Think about what that looks like on an actual job site.
It's huge.
You are talking about falling past 2 entire stories of a building before your hand even closes to grab that railing you thought was going to save you.
Wow.
By the time your brain tells your hand to grab the rail, that rail is 20 feet above your head.
That is wild.
This is the fundamental foundational reason why we rely on math engineering and passive fall protection systems rather than human reflexes.
Because human reflexes are simply too slow to negotiate with gravity.
Exactly. They are useless in that scenario.
Okay, so if we can't rely on reflexes, we have to rely on the math.
Right.
And for anyone studying for their ASP exam, or frankly, anyone designing a safety system, this means we have to rely on the kinematic equations.
The foundational formulas of motion.
Right. These are the mathematical tools we use to predict the exact behavior of an object, or in our case, a person in free fall.
Yes.
We have 4 basic kinematic equations that map out displacement, velocity, time, and acceleration. But before we just start reading formulas, let's actually define what these variables mean in the real world.
That is a crucial step. If you just try to memorize the letters, the exam will completely trick you. You need to know what the letters represent physically.
Okay, so let's start with D.
Right, so D stands for displacement, or in our context, the vertical distance of the fall. This is usually expressed in feet or meters,
Makes sense. And then we have T.
which is simply time, always measured in seconds.
Easy enough. Next is a P, which is acceleration.
Right, and on Earth, gravity accelerates a falling body at a constant rate of 32.2 feet per second squared, or if you are using metric, 9.8 meters per second squared.
I want to pause right there on that acceleration number because 32.2 feet per second squared is one of those phrases we hear in high school physics and just blindly accept without thinking about what it actually means.
Right, people just memorize the number.
Yeah, but what does the squared part actually do? It means that for every single second you fall, your speed increases by an additional 32.2 feet per second.
Exactly, it compounds.
It is not a steady constant speed. You don't just fall at 32 feet per second the whole time. It's an accelerating exponential nightmare. The longer you fall, the faster you gain speed.
That is a brilliant way to explain it. It is the compounding interest of physics, and the debt is kinetic energy.
Ooh, I like that.
And that brings us to our last 2 variables to complete the set. We have V sub I, which is initial velocity, and V sub F, which is final velocity.
Now, in almost all of the fall protection scenarios we are looking at from the sources, the worker starts from a standstill, right?
Generally, yeah.
They are just standing on a beam and they slip. So their initial velocity, their V sub I, is going to be 0.
Correct. Unless they are actively jumping upwards or being forcefully thrown downwards, the initial velocity is 0.
Okay.
And there is one more critical mathematical convention to remember from the Yates text, especially when you are actually doing the algebra.
What's that?
When an object falls downward due to gravity, the distance or displacement is technically expressed as a negative number.
Oh, right. Because of the axis.
Exactly. If you fall 27 meters, it is mathematically a negative 27 meters of displacement because you're moving downward relative to your starting position on the y-axis.
Okay, that makes complete sense. Let's actually put these variables to work. I don't want to just talk about the theory. I want to walk through a practical calculation straight from the sources so we can see how this actually plays out.
Let's do it.
The text gives us a scenario of a 62-foot fall. Let's say a worker falls from a roof that is 62 feet up. I want to know exactly how long this worker is in the air and exactly how fast they are traveling when they impact to the ground.
Okay. We can solve this step by step using one of the primary kinematic equations.
Okay.
The relationship is this. Displacement equals initial velocity times time plus 1/2 acceleration times time squared.
Okay, let me write that out. So it is d equals v sub I times t plus 1/2 times t squared.
Perfect.
Okay, let me just try to wrap my head around this math. You said earlier that since the worker slips from a standstill, our initial velocity, the v sub I, is 0.
Right.
So if I multiply 0 by whatever the time is, well, it's just 0.
Exactly.
That whole first chunk of the equation, the v sub I times t, just vanishes completely.
It drops right out. You are left with a much simpler, cleaner formula to work with. You just have d equals 1/2 of t squared.
Oh man, that is way less intimidating. Okay, so now I plug in our knowns. The distance d is 62 feet.
Yeah.
The acceleration of gravity is roughly 32.2 feet per second squared. But looking at the Yates text, they simplify it to just 32 to make the algebra a bit cleaner for the example.
Right, they round it down just to keep the numbers round.
So the equation looks like this. 62 equals 1/2 times 32 times t squared.
Perfect. Now walk us through the rest of the algebra.
All right, well, half of 32 is 16. So the equation simplifies down to 62 equals 16 times t squared.
Good.
Now I need to isolate the time t. So I divide 62 by 16. Let me think here. 62 divided by 16 is exactly 3.875.
You got it.
So now I have t squared equals 3.875. Now this is where I always used to get stuck in school. Time is squared. So to find the actual time in seconds, I just have to take the square root of 3.875, right?
That is exactly right. And the square root of 3.875 comes out to approximately 1.96 seconds.
1.96 seconds. Wow.
It's fast.
Let's just sit with that for a moment. A 62-foot fall. That is roughly equivalent to falling off the roof of a 6-story commercial building.
A massive drop.
And the entire event, from the exact moment your boot slips off the edge to the moment you impact the pavement, is completely over in less than 2 seconds.
You barely have time to take a single breath.
That is the sheer brutal efficiency of gravity.
It is terrifyingly fast. But we aren't quite done with the scenario. We found the time in the air. But to truly understand the physics of the hazard, we need to calculate the final velocity at impact.
We need to know how fast they're going.
Exactly. We need to know how fast that worker is traveling when that 1.96 seconds finally runs out.
Okay. For that, we use a different kinematic equation, right?
Yes.
Final velocity equals initial velocity plus acceleration times time. So v sub f equals v sub I plus a times t.
Correct.
And just like since the initial velocity is 0, that part just drops out again, leaving us with just final velocity equals acceleration times time.
Precisely. So you take your acceleration, which we are calling 32 feet per second squared, and you multiply it by the time we just calculated, which is 1.96 seconds.
Okay, so 32 multiplied by 1.96 gives us a final velocity of 62.72 feet per second.
Right.
That means at the exact moment of impact, the worker is traveling at over 60 feet every single second.
It's moving incredibly fast.
That is a massive, almost incomprehensible amount of kinetic energy that the human body is about to be forced to absorb.
It is, but as safety professionals, we often run into a communication problem right here.
What do you mean?
Well, telling a worker or a site manager that a fall results in an impact of 62 feet per second, it doesn't usually elicit the reaction we want.
Oh, because the units don't make sense to them.
Exactly, because human beings don't naturally intuit what feet per second feels like. We don't drive our cars in feet per second. We think and we feel in miles per hour.
Oh, that is a really great point. Let's translate this into something visceral then. Let's look at another specific example from the SPAN CSP exam prep materials provided in our sources.
Good idea.
Imagine a 170-pound worker falling off a 20-foot scaffold.
A 20-foot fall is incredibly common in the construction industry. It might not sound nearly as dramatic as falling 62 feet off a 6-story roof. And sometimes workers get a little complacent at that height.
Right, they think, oh, it's just 2 stories.
Exactly. But the physics are just as unforgiving. If we run those exact same kinematic equations for a 20-foot drop, and we can ignore air friction here because at this short distance and relatively low speed, it is mathematically negligible, we find the velocity just before impact.
And what is it?
Well, if we do the mathematical conversion from feet per second to miles per hour, the math shows us that this 170-pound worker will impact the ground at approximately 25 miles per hour.
25 miles per hour. Okay, let's put that into context.
Please do.
If you were driving a car down your neighborhood street at 25 miles per hour, and you took off your seatbelt and you drove straight head-on into a solid brick wall,
It would be disastrous.
you would absolutely expect to sustain serious life-threatening injuries. Your head would hit the steering wheel, your ribs would crack, your internal organs would suffer major trauma. Everyone intuitively understands that a 25-mile-per-hour car crash into a wall is a severe emergency.
No one questions that.
But because a worker is falling vertically through empty space, we somehow mentally discount the severity. We think, oh, it's just 20 feet.
Just a quick drop.
Right. But the math proves that a 20-foot fall is literally identical to a high-speed vehicle collision into a brick wall, just without the metal chassis of the vehicle to crush and absorb the energy for you.
Yeah, that's exactly it.
You are the crumple zone.
That is a phenomenal way to frame it. You are the crumple zone. And that realization forces us to shift our perspective entirely. Because as the old, somewhat dark saying goes, it isn't the fall that kills you, it is the sudden stop at the end.
The impact.
Right. We have successfully used kinematics to calculate the terrifying speed of the descent. But the speed itself doesn't actually cause the injury.
Right. I mean, astronauts travel at 17,000 miles per hour in orbit, and they are perfectly fine.
Exactly. The injury is caused by the change in speed. Now we have to look at the extreme forces of deceleration on the human body.
The sudden stop. This is where the abstract physics of gravity suddenly meets the very fragile reality of human physiology.
Yes, it is.
Let me offer an analogy to try and help visualize exactly what we were talking about here with deceleration.
Go for it.
Imagine you are standing on a platform 10 feet in the air and you fall off, but you land perfectly onto a thick, bouncy trampoline mattress.
Okay, sounds fun, actually.
Right? You bounce a couple of times, you get up, and you walk away laughing. Now imagine falling that exact same 10 feet onto a hard concrete floor.
Not fun at all.
You are leaving the site in an ambulance, likely with broken bones.
Yeah.
But here's the thing. Your final velocity, your speed right before you hit, was exactly the same in both scenarios.
That's true.
The kinetic energy your body built up from the fall was exactly the same. So why is the outcome so drastically different?
It all comes down to two highly interconnected variables, stopping distance and deceleration rate.
Okay, break that down.
When you hit the trampoline, the moment your feet touch the fabric, you don't instantly stop. The springs stretch, the mat deforms, and your body continues to travel downward for maybe 2 or 3 feet before coming to a complete final halt.
Right, you sink into it.
Exactly. That physical distance extends your stopping distance. But when you hit a concrete floor, your stopping distance is essentially zero. Concrete doesn't deform. You start instantaneously.
Let's look at the mathematical formula for deceleration from the Brouwer Safety and Health for Engineers text to see how this works mathematically.
Good, let's pull that up.
Deceleration, which we will call A equals velocity squared, divided by 2 times the stopping distance. So the formula is A equals V squared over 2S.
Now, if you look closely at that equation, the relationship between the variables tells the whole story. The stopping distance S is in the denominator. If your stopping distance is a generous 3 feet, like on the trampoline, the denominator is relatively large, which makes the resulting deceleration rate much smaller and manageable.
Because dividing by a big number gives you a smaller number.
Right, exactly. But if your stopping distance is a tiny fraction of an inch, like hitting unyielding concrete, that denominator is incredibly small.
Yeah.
And mathematically, when you divide by a tiny fraction, your result explodes.
It shoots through the roof.
Yes. It makes the deceleration rate astronomically high. You are scrubbing off all of that built-up velocity in a matter of milliseconds.
And once we know that violent deceleration rate, we can calculate the actual force of impact, or F sub I, that the body experiences.
Right.
The formula for this is F sub I equals weight times deceleration divided by gravity. F sub I equals W times A over G.
Yes.
This means the sheer force applied to the worker's internal organs and bones is directly tied to 2 things: how much the worker physically weighs and how violently they're decelerating.
And we measure the violence of that deceleration in g-forces.
Right, G-forces.
By taking the deceleration rate and dividing it by the standard acceleration of gravity, that A over G part of the formula you just read, we find out exactly how many Gs the worker is pulling during the arrest of the fall.
Okay.
And this isn't just an abstract engineering number. When we talk about high G forces in a fall context, we are talking about the mechanical limits of human tissue.
We're talking biology now.
We are talking about organs tearing away from connective tissue bones, fracturing under compressive loads, and blood vessels just rupturing.
Which naturally begs the question, right? How many G-forces can a human body actually take before severe irreversible injury occurs?
It's a critical question.
I mean, we hear about fighter pilots pulling 9 Gs in a sharp turn, but what happens when it's a sudden jarring impact?
Well, the human tolerance for sudden deceleration is lower than most people think. According to the ANSI, a 10.14 standard cited in the text, there are strict biologically determined limits, and they depend heavily on the type of equipment the worker is wearing.
Okay, what are the limits?
If a worker is wearing a standard body belt, which is literally just a belt that goes around the waist, which used to be very common in the industry, they are legally and physiologically limited to a maximum deceleration force of just 10 Gs.
Just 10.
Just 10. But if they're wearing a modern full-body harness, they can withstand up to 35 Gs.
Wait, hold on. Let me make sure I'm understanding this correctly. 10 Gs for a waist belt, but 35 Gs for a full-body harness.
That's right.
That is a massive discrepancy. Why can a worker magically survive more than 3 times the G-force just by changing the configuration of the nylon straps they are wearing?
Well, it has nothing to do with magic and absolutely everything to do with the physical distribution of force across human anatomy.
Okay, explain that.
Think about what a body belt is. It is a narrow band of material wrapped entirely around the soft abdomen and the lower lumbar spine.
It's right around the middle.
When that belt catches a falling worker, it focuses the entirety of that brutal stopping energy into that one narrow line. It acts almost like a wire attempting to cut into the body. Oh man, that sounds awful.
It is. All that kinetic energy violently compresses the soft internal organs, your liver, your spleen, your kidneys, and it acts as a fulcrum on the spine, causing severe internal trauma and often literally folding the worker in half backwards.
Oh, wow.
The fundamental physics formula to remember here is F equals SA, where force equals stress applied over an area. Or if we rearrange it to understand what the body actually feels, stress equals force divided by area.
Oh, I see. If the area is incredibly small, like a 2-inch wide belt, you are dividing that massive force by a tiny number.
Exactly.
So the resulting localized stress on the tissues is absolutely catastrophic.
Precisely. You are putting thousands of pounds of force onto a few square inches of soft tissue. A full-body harness, on the other hand, is specifically engineered to manipulate that exact formula.
It increases the area.
It does. It distributes that arresting force over a much, much larger surface area. It wraps around the thighs, the pelvis, the chest, and the shoulders.
And those are stronger parts of the body, right? Yes, these areas house the strongest, most robust, bony structures of the human body. The femur, the pelvic, girdle the ribcage. By drastically increasing the area over which the force is applied, you dramatically reduce the localized stress.
That makes perfect anatomical sense.
That is why a worker in a harness can survive a 35 G deceleration without lethal internal injuries, while a body belt wearer would suffer fatal trauma at a fraction of that force.
Okay, let's take these G-forces out into the field with another practical calculation. Let's walk through an example from the SPAN CSP exam prep so we can see how an auditor or safety professional would actually calculate this on site.
Let's do it.
We have a 180-pound worker. They're wearing a compliant fall arrest system. They slip, and they free fall 6 feet before their lanyard catches them and arrests the fall.
Okay, pretty standard scenario.
The engineering math tells us that the total arresting force placed on the anchor point during that exact catch is 900 pounds. So how do we figure out the G-forces the worker's body actually experiences?
It is a surprisingly straightforward calculation once you have those numbers. We take the total arresting force generated by the fall, and we divide it by the worker's static weight.
Okay.
So you take the 900 pounds of force divided by the 180-pound worker, and that equals 5 total Gs.
5 total Gs. But we need to be incredibly clear about what that actually means physiologically. Right now, sitting in a chair or standing on the ground listening to this, you and I are experiencing 1 G.
Right.
That is just standard resting gravity pulling us toward the center of the earth.
Correct. So if the total force of the arrest is 5 Gs, the worker is experiencing 4 additional G forces entirely beyond the standard gravity they always feel.
4 extra Gs.
Yeah. It means at the exact split-second moment the lanyard goes tight, their body suddenly weighs 5 times its normal weight. If their arm weighs 10 pounds, normally it suddenly weighs 50 pounds. Their internal organs, their blood volume, their brain sitting inside their skull, everything suddenly experiences a 5-fold instantaneous increase in weight, pulling violently downward against the straps of the harness.
That sounds incredibly painful, even if the math says it is survivable.
It is definitely traumatic.
And this is exactly why OSHA steps in with strict regulatory limits on the maximum resting force equipment is allowed to generate. The text outlines the OSHA mandates, and they draw a very hard, non-negotiable line in the sand.
Very hard.
When an employer is using a body belt system, in the rare cases they are still permitted for positioning or fall arrest, the system must be engineered to limit the maximum arresting force to exactly 900 pounds, period.
Nothing more.
But when using a full-body harness, because of that superior force distribution over the skeletal structure we just talked about, OSHA allows the maximum arresting force to reach up to 1,800 pounds.
And it is vital to understand that those limits are not just arbitrary numbers pulled out of thin air by a regulator in Washington.
They aren't just making it up.
No, they are carefully calculated thresholds derived directly from the physiological limits of human tissues and bones. If an employer bypasses those limits or uses a rigged system that allows, say, 2,500 pounds of arresting force before it fully stops the worker, they are not just getting an OSHA citation.
What are they doing?
They are practically guaranteeing internal hemorrhaging catastrophic organ damage or spinal failure for their worker. The equipment might stop them from hitting the ground, but the equipment itself will kill them through deceleration trauma.
And hitting the ground is the absolute worst-case scenario. It is the ultimate failure of the system.
Without a doubt.
Which brings up a terrifying thought. We have spent all this time talking about designing equipment that stretches and yields to keep those G-forces below the OSHA limits.
Right, to keep the forces low.
We want the equipment to stretch to buy a stopping distance. But if the equipment stretches and the worker falls further during the arrest, doesn't that mean they're getting closer to the ground?
Yes, it does.
How do we ensure they don't hit the concrete while the equipment is busy stretching?
That is the perfect question, and it is the most common tragic miscalculation in an entire field of fall protection.
Really?
Yes. People assume that just putting on the harness and clipping the lanyard makes them inherently safe. They never do the geometry to ensure the equipment actually has enough physical room in the air to fully deploy.
Exactly. Let me play the devil's advocate here and push back with a scenario I see all the time on job sites. I really want to break this down.
Let's hear it.
Let's say I'm on a construction site. I am working on an elevated platform that is exactly 12 feet off the ground.
12 feet, okay.
I am wearing my compliant full-body harness, and I clip my standard 6-foot lanyard to an anchor point right at my feet on the platform deck.
Tied off at your feet, got it.
Right. I do the quick mental math in my head. I am 12 feet up in the air, my lanyard is only 6 feet long. Even if I fall, the lanyard will catch me after 6 feet, leaving me dangling 6 feet above the concrete. I have 6 feet of clearance to spare. I am perfectly safe, right?
That is what I call the ultimate one-size-fits-all fallacy, and it is a deadly assumption.
A deadly assumption.
In that scenario, you are absolutely not safe. If you fall off that 12-foot platform, you are going to impact the lower level with bone-shattering force.
But the math in my head made sense.
Your mental math is flawed because it ignores the actual mechanics of how the equipment arrests a fall. To understand why you hit the ground, we have to dismantle your assumption using the total fall distance formula provided in the ASP exam sources.
Okay, let's break down the variables of the total fall distance formula. The formula states that total distance equals employee height, which we will call EH,
Right.
plus lanyard length, which is LL, plus deceleration device length, DD, plus a safety factor. So EH plus LL plus DD plus safety factor. Why are there so many pieces to this?
Because every single piece represents a physical distance, the worker travels downward before coming to a final stop. Let's walk through why each of those matters.
Yeah.
First, employee height, or EH. Why does your height matter? Because when you clip a lanyard at your feet, the attachment point on your harness is the D-ring located high on your upper back between your shoulder blades.
Oh, right.
When you fall, your body orientates vertically. Your feet are going to be extending several feet below that D-ring. The lanyard stops the D-ring, but your feet are much lower.
Okay, that makes complete sense. I didn't think about where my feet were relative to the attachment point.
Most people don't.
Then we have the lanyard length LL. That's the obvious one. A 6-foot lanyard means you literally free fall for 6 vertical feet before the slack is gone, and it even begins to pull tight to start arresting the fall.
Right, exactly. Next is the deceleration device length, the DDs. We just talked extensively about how hitting concrete is bad because the stopping distance is 0.
We need to extend the stopping distance.
Right, so to prevent that instantaneous stop and keep the G-forces below OSHA's 1,800-pound limit, modern lanyards have built-in shock absorbers.
Those little brick things on the lanyard, right?
Yes. This is usually a packed brick of folded webbing that literally rips open under force to extend the stopping distance. But when it rips open, the lanyard gets longer. According to OSHA Subpart M, a deceleration device is allowed to extend an additional 3.5 feet during the arrest.
And finally, we have the safety factor. The sources indicate we must add an automatic, non-negotiable 3-foot safety factor to the calculation.
Non-negotiable.
Why 3 feet? Because the real one isn't a perfect physics simulation. Things stretch. The heavy nylon webbing of the harness stretches tightly around your body under the force of the fall.
Yeah, pulls tight.
The anchor point on the steel beam might deflect slightly. The D-ring on your back might slide up a few inches. You mandate a 3-foot buffer zone so that even at absolute maximum extension, the worker's boots don't even brush the concrete.
Exactly. So let's run the real terrifying math on your 12-foot scenario using the specific numbers from the YETS text.
Let's do it.
We have a 6-foot-tall employee. That is an EH of 6. We have a standard 6-foot lanyard attached at the feet. That is an LL of 6.
Okay.
We have a fully deployed shock absorber, adding another maximum of 3.5 feet. That is a DD of 3.5. And we add our mandatory 3-foot safety factor.
I am adding this up right now. 6 feet for my height, plus 6 feet for the lanyard is 12.
Right.
Plus 3.5 feet for the shock absorber ripping open is 15.5.
Keep going.
Plus the 3-foot safety factor, that brings the total fall distance to 18.5 feet.
That is the total vertical distance mathematically required to safely arrest the fall, allow the equipment to do its job, and leave the worker suspended safely above the ground. 18.5 feet.
Wow.
But in your scenario, the worker was standing on a platform only 12 feet off the ground.
18.5 feet of required space to let the equipment work, minus the 12 feet of actual space I have before I hit the concrete. The system fails by 6.5 feet.
It fails completely.
The deceleration device never even gets the chance to fully deploy to save me because I impact the lower level first.
That is the tragic reality on far too many job sites. The worker dies or is catastrophically injured while wearing thousands of dollars of state-of-the-art, perfectly compliant fall protection equipment simply because no one did the basic addition of clearance geometry.
Is basic addition.
This specific math, this calculation of clearance is literally the difference between life and death. You cannot guess. You cannot eyeball it. You have to calculate.
I really want anyone listening right now to deeply internalize this. When you are taking your ASP exam, they will absolutely test you on this to see if you fall for the mental trap.
It definitely will.
And when you are standing on a site looking at a crew tying off, do not just look at the 6-foot lanyard and assume they're fine. You must look at the whole equation. EH plus LL plus DD plus safety factor. It is non-negotiable.
You have to see the whole picture.
If you don't have 18.5 feet, you have to engineer a different solution. You have to raise the anchor point above their head or use a shorter system.
And that leads us to the final massive point of failure we need to discuss today.
What's that?
Because even if you do the clearance geometry perfectly and you calculate the deceleration G-forces perfectly so the worker survives the arrest, none of it matters if the hardware itself explodes under the pressure.
Oh, the anchorages.
The anchorages, the ropes, and the physical dynamic loads.
Right. To ensure the clearance math works, the physical equipment must actually survive the kinetic event. If the anchor rips out of the concrete or the lanyard snaps in half, all the clearance in the world won't save you.
According to the OSHA standards detailed in our sources, anchorages used for the attachment of personal fall arrest equipment must be completely independent of any anchorage being used to support or suspend platforms.
You can't tie off to the same thing holding up your scaffold.
Correct. And crucially, they must be capable of supporting at least 5,000 pounds per employee attached. Or alternatively, they must be part of a complete personal fall arrest system, which maintains a safety factor of at least 2 under the direct supervision of a qualified person.
Okay, stop right there. I have to push back on this because intuitively it sounds insane. 5,000 pounds.
It sounds like a lot.
Why on earth does an anchor need to hold the weight of a heavy-duty pickup truck? The worker only weighs 200 pounds. Even if he is carrying a massive heavy tool belt, maybe he weighs 250 pounds max.
True.
Why does OSHA force us to over-engineer an anchor to hold 5,000 pounds just to catch one single guy?
That is the perfect question, and it is a point of confusion for a lot of people entering the field. It brings us to the fundamental difference between a static load and a dynamic load.
Okay, static versus dynamic.
When a 200-pound person is just hanging motionless from a rope, they exert a static load equal to their weight. The anchor only feels 200 pounds of pull. But a fall is not static. A fall is a violent dynamic event.
Right.
Using principles from the Bechtel rigging handbook included in our sources, we can understand this through the lens of dropped loads.
Okay, let's unpack this Bechtel rigging concept.
Yeah.
How does rigging a crane load relate to a falling worker?
Let me use an analogy. If I take a 15-pound bowling ball and I gently toss it to you underhand from 2 feet away, you can catch it easily.
Yeah, no problem.
Your arms absorb the low dynamic load, but if I take that exact same 15-pound bowling ball and I drop it from a second-story window directly into your arms,
Oh, man.
it is still a 15-pound ball. Its static weight hasn't changed, but catching it will likely break your arms.
Because of the instantaneous deceleration. The kinetic energy built up during the fall has to go somewhere when it stops.
Exactly. The Bechtel text explains that when a load is dropped in a free fall, and then the system suddenly engages, causing virtually instantaneous deceleration, the load does not just politely stop.
It violently transfers the energy.
Yes, that massive kinetic energy creates an instantaneous acceleration that exponentially multiplies the force placed on the entire system. The handbook shows calculations where a dropped load experiencing rapid deceleration creates an impact force that can be hundreds or even thousands of % higher than the static weight of the object.
So when our 200-pound worker falls 6 feet and violently hits the end of that lanyard, they aren't a 200-pound weight anymore. They're a kinetic wrecking ball.
Exactly, a human wrecking ball.
The anchor point isn't catching 200 pounds. It is catching the multiplied force of that sudden deceleration. The system must have sufficient strength to withstand twice the potential impact energy of an employee free-falling 6 feet.
That is the core of the rule.
That 5,000-pound rule is there because dynamic loading turns a human into a massive system-destroying force for a split second.
That is exactly it. And to predict exactly how much force that human wrecking ball will generate on the system, safety engineers use the maximum arrest force, or MAF, empirical formula.
The MAF.
The Brower text provides this formula, and frankly, it is an algebraic beast. The formula is MAF equals weight multiplied by a complex bracketed calculation involving the square root of 1 plus 1.45 times the rope modulus times the fall factor times the square root of the weight divided by a conversion factor.
Wow. Okay, I can guarantee you that absolutely no one is doing that specific math in their head while standing on a scaffold in the freezing rain.
Definitely not.
But as safety professionals, we don't necessarily need to memorize the unreadable algebra to be effective. We need to understand conceptually what those variables are actually doing to the worker's body. Let's break them down intuitively.
Let's do it.
Weight W makes obvious sense. A heavier guy generates more kinetic energy, resulting in more force. But what about the rope modulus K? What does that actually mean?
Think of the rope modulus, or K, as representing the stiffness or the spring rate of the lanyard material. It measures how much the material fights back against being stretched.
Okay, like rubber versus steel.
Exactly. If you were to use a steel cable as a lanyard, the modulus is extremely high. Steel doesn't stretch easily, so when the worker hits the end of the cable, the stopping distance is near zero, and the arrest force spikes violently.
Right.
But if you use nylon webbing, the modulus is lower. It stretches. That stretch acts exactly like a spring, absorbing kinetic energy and physically lengthening the deceleration time, which dramatically lowers the MAF. The stretch buys you time.
That makes perfect sense. And then there is the fall factor F. The text defines this as H over L, which is the vertical fold distance permitted divided by the total active lanyard length.
This is a highly critical ratio in both rock climbing and industrial fall protection.
Why is that?
A higher fall factor means a much more violent arrest because you have fallen further relative to the amount of rope you have available to absorb the shock.
You've generated more energy, but have less material to soak it up.
Precisely. All these variables, the weight, the stiffness of the material, the distance of the fall, they all interact in that complex formula to generate the maximum arrest force.
And remember, OSHA explicitly mandates that this force cannot exceed 1,800 pounds for a full-body harness.
Right.
So the engineering challenge is, how do equipment manufacturers guarantee they keep the MAF below 1,800 pounds when A heavy 250-pound worker takes a maximum 6-foot plunge.
How do they do it?
The answer is they engineer the lanyard to intentionally break apart.
The shock absorbers. I was hoping we would get to this because the engineering here is fascinating.
It really is. The Brower text details 2 specific types of shock absorbers built into these systems to artificially extend that stopping distance. The first is called tear the stitches.
Yes. In a tear the stitches absorber, the heavy nylon webbing is folded over on itself multiple times and sewn together with a very specific mathematically calculated thread strength.
Okay.
When the worker falls and the dynamic force hits exactly 550 pounds, those stitches begin to violently pop and tear apart.
They just start ripping.
As they tear one by one, the tearing action absorbs the massive kinetic energy of the fall, keeping the force on the worker's body relatively steady.
Wow.
The text notes that this tearing action adds exactly 3.6 feet of elongation to the system.
And the second type mentioned is tear the fabric. This one is woven together in a structurally different way that requires more initial force to activate.
Right, it's stronger initially.
It has a higher starting force of 1,000 pounds before the fabric itself begins to tear apart, and the text notes it adds 2.9 feet of elongation. But regardless of whether it tears stitches or tears fabric, both designs have the exact same fundamental goal: bleed off the kinetic energy into the destruction of the lanyard so the worker's internal organs don't have to absorb it.
And this brings us right back to the Subpart M mandates from OSHA, which essentially codify all the math we've talked about today.
Let's reiterate them clearly, because they are the golden rules of fall arrest design.
Let's hear them.
First, the harness system must be rigged so an employee cannot physically free fall more than 6 feet. Second, they cannot contact any lower level, that is our critical clearance math.
Right, the geometry.
Third, the system must eventually bring the employee to a complete suspended stop. And finally, the maximum deceleration distance, the actual distance it takes for those stitches or fabric to rip apart and stop the fall, must be strictly limited to a maximum of 3.5 feet.
It is a delicate, tightly controlled dance of physics. You have to let them fall just a little bit to allow the equipment to stretch and absorb the load, but not too much, or they hit the concrete. You have to stop them fast enough to keep them suspended, but not too fast, or the G-forces exceed 35 Gs and cause massive internal trauma.
The sheer amount of engineering testing and math behind that simple nylon strap you wear on your back is truly mind-blowing.
It absolutely is. And it relies entirely on safety professionals, site managers, and engineers doing the math correctly every single time they set up a system.
Every single time.
There is zero room for error estimation or guesswork when you are dealing with gravity.
Which brings us to the end of our journey through the math today. Let's briefly recap what we've covered in this edition of QHSE Talks.
It's been quite the journey.
We started by looking at the descent, calculating the terrifying compounding speed of free fall using the kinematic equations, realizing that a mere 20-foot fall is biologically identical to hitting a brick wall at 25 miles per hour.
Terrifying reality.
We then look closely at the sudden stop mapping out human G-force limits and understanding the anatomical reasons why a harness can safely take 35 Gs, while a waist belt can only take 10.
Force distribution is key.
We walk through the critical geometry of survival, calculating total clearance distance and exposing the deadly 12-foot fallacy.
18.5 feet of clearance is what you really need.
And finally, we look at the physical hardware, exploring dynamic loads, the bowling ball analogy, and why an anchor must be strong enough to withstand 5,000 pounds just to catch a single falling worker.
It is an incredible amount of math, but it is math with a profound life-saving purpose. However, I want to leave anyone listening with a final, somewhat provocative thought to ponder as they head back out to the site.
What's that?
We have spent this entire session proving that through kinematics and engineering, we can successfully design a system to stop a human being from hitting the ground. The math works.
It definitely works.
But I want you to truly consider the trauma of the arrest itself. If an employee falls and they endure 1,800 pounds of arresting force and experience 35 Gs of deceleration, well, the math dictates that they survive.
Right, they don't hit the ground.
They don't hit the ground. But make no mistake, their body has still experienced a violently extreme, highly traumatic physical event. They may survive the fall, but they might not walk away uninjured.
They could still be badly hurt.
They could suffer severe bruising, musculoskeletal strain, or suspension trauma. It challenges all of us as safety professionals to remember a fundamental truth. Fall protection, the harnesses, the lanyards, the shock absorbers, the 5,000-pound anchors, is the absolute last line of defense.
The last resort.
Fall prevention, using solid guardrails covering holes and utilizing careful pre-planning to ensure the worker never even enters free fall to begin with, must always, always remain our ultimate goal.
That is an incredibly powerful point to end on. Surviving a fall in a harness is absolutely not the same as never falling at all. We want to thank you for joining us on this edition of QHSE Talks.
It's been great.
Whether you are taking your ASP exam tomorrow or inspecting a job site this afternoon, keep studying, keep doing the math, and most importantly, take these formulas out into the field to keep your team safe. Until next time, keep your eyes open and your anchor points solid.